Okay, so next up we look at indirect proofs, and indirect proofs are kind of fun, and because what you're going to do is you have your theorem where you have A implies B, you're going to assume not B, and you're going to utilize all your A to arrive at a contradiction. So assume not B, and then with all conditions of A, get to a contradiction. Now, a contradiction is going to be in your notes written as an upside down T. It is also sometimes written as your lightning bolt. Okay. And the idea is if you get to a contradiction, that means that your assumption is incorrect. And this comes from your logic statements. So you should reach logic statements in maths by now, or have already done it, or will reach it soon. And it comes from that idea. The idea is if you get a contradiction, then your assumption is incorrect. And then you've proven that A implies B. Okay, so let's go ahead and do a theorem statement and an example of proving it indirectly. So the theorem we're going to look at is let the order of the graph be equal to n, and then we're going to have a vertice, which is element of the vertice set. Then the degree of the vertice must be greater than or equal to n over 2 for g, and then g is connected. So if the degree of any vertice in your graph is greater than n over 2, then your g is going to be connected. So theorem, if the order of g equals to n, if v is the element of the vertice set of the graph, and the degree of v is greater than or equal to n over 2, then g is connected. Okay, so we're required to prove that if the degree of v is greater than or equal to n over 2, then g is connected. To prove this indirectly, we have to assume not B and show a contradiction. So we have to prove that, or we have to assume that G is disconnected, and then show that if G is disconnected, we can't get the degree of V to be greater than or equal to n over 2. There's going to be some situation where there is a contradiction there. And why we're going to use this proof as indirect is because we already know something about connected components. Remember, we just did that in the direct proofs where we showed that we had the directed components. If the order of g is equal to n and both the components are the same size, then the degree of x is less than or equal to n over 2 minus 1. And then we also showed that the smallest component, so the smallest component is going to have the degree of x being less than or equal to n over 2 minus 1. And that is if it's disconnected. So now we have something there because we can assume that G is disconnected, and then we're like, okay, if it's disconnected, let's look at the component of the smallest order. And we're like, well, if the component of the smallest order, then the degree of x must be less than or equal to n over 2 minus 1. And then we're like, straight away, there's a contradiction because we stated that the degree of v is greater than or equal to n over 2, the degree of any vertice in that situation. So we know that it's not going to be greater than or equal to n over 2, and therefore there's a contradiction there. So let's go ahead and do that. So we have a proof. We're going to have let G be disconnected. So remember, the whole idea for indirect is that we assume not B, and B in this case is G is connected. So we assume that G is disconnected. Then we're going to take just some information that we already knew. So we already knew that if we have a disconnected graph, we have the components. We have the smallest component has a degree of x less than or equal to n over 2 minus 1. So let's write that down. Let x be an element of the component of smallest order. And just FYI here, and just a reminder that obviously as you're new to this, it's not going to necessarily come to you straight away. The whole idea is to start thinking about it, to start connecting your past theory to prove something that you want to do. So it's a puzzle piece, you're slowly building up the puzzle pieces, and you're building up your skills to solve these puzzles. So if you can't see it straight away, that's perfectly fine. It's like just start seeing how we take past theory that we know to solve this. And sometimes doing that is going to take a long time. So any mistakes are going to be made, but then you just keep on at it until you eventually get somewhere where you prove that it is true or not. Okay, so back to the proof. So we have G is disconnected. That was our assumption. So we're saying let G be disconnected. And we now want to find a contradiction. So we want to find a contradiction. The thing that we're going to contradict is the degree of V must be greater than or equal to n over 2. So now we look at past information that we know that if we have a disconnected graph and we have it in components, the degree of this the maximum degree of the smallest component is going to be less than or equal to n over 2 minus 1. So let's bring that in. Okay, then the degree of x is less than or equal to n over 2 minus 1. But n over 2 minus 1 is less than or equal to n over 2, which is a contradiction. Because we're saying that any arbitrary vertice of VG is such that the degree of those vertices are greater than or equal to n over 2. As all vertices of G satisfy the degree V greater than or equal to n over 2. Therefore, because we found a contradiction, our assumption must be incorrect. Therefore, G is connected. So let's just go through that again. We have a theorem that says let the order of G be equal to n. If V is the element of the vertice set, so it's any arbitrary V, and the degree of V is greater than or equal to n over 2, then G is connected. So because V is any arbitrary vertice, all the vertices of G must have a degree of V of which is greater than or equal to n over 2 for it to be connected. So then we assume that G is disconnected. And we use our previous information that we have, now that we've learned it, where we have, if we have a disconnected graph, the components of the disconnected graph are such that the smallest components, degrees of the vertices must be less than or equal to n over 2 minus 1. And we utilize that to create a contradiction. Then we say, okay, there's a contradiction, therefore our assumption is incorrect and G is connected. Okay, before we do the next theorem, we actually have to bring in a definition, and the definition is a bridge. And a bridge is pretty much exactly like you'd see a bridge in regards to the fact that if you have a connected graph, and it's a situation where if you remove that edge, your graph becomes disconnected. So say you have a graph like this. This one over here, if you move it, your graph becomes disconnected. So that is a bridge. That's the idea behind it. Or, for example, again, let's not make it so blatantly clear. Actually, let's keep on making it blatantly clear so that you can actually see the process. Okay. What are bridges on that one? So, if you remove this one here, your graph becomes disconnected. So that's a bridge. Let's go back. Let's unhide that. If you move this one here, your graph becomes disconnected. So that's also a bridge. And the same thing over here. If you remove that one there, your graph becomes disconnected. So that's a bridge as well. Same situation happening there. So it's any edge, which if you remove that edge, your graph becomes disconnected. So in other words, if it's involved in a cycle, it's not a big deal, it's not going to be a bridge. If it's not involved in a cycle, it's going to be a bridge. And this is where we get to the situation of let G be a connected graph with E an element of the edge set, and if E is a bridge, then E is not part of any cycle. And if E is not part of any cycle, then E is a bridge. So it's going to be a two-first situation. So let's actually just discuss that first. When I speak about that, when you have a situation where A implies B, but B also implies A, that's the converse. So if you have A implies B, the converse of this is B implies A. And the idea behind that is you have this situation then. The downside to that situation is if you're proving it, you have to prove it in both directions. So just a heads up, so that's the sucky fact about it. But it is nice in that if you have the conditions of B, you know A is for definite. And if you have the conditions of A, you know B is for definite. So you have this situation of you can utilize it in either way. Or you know that once you have the conditions of one, it's definitely going to have those other conditions. Right. So let's go ahead and write that theorem statement. So the first thing, again, let's just write the definition of a bridge. So remember the bridge. Let G be a connected path, a connected graph, sorry, not path. And E is an element of the edge set. E is a bridge if G minus at E is disconnected. Okay, so it disconnects the graph. Then we have our theorem. And our theorem states, let G be a connected graph with E an element of the edge set. So let G be a connected graph with E element of the edge set if E is a bridge, then E is not part of any cycle, and if E is not part of any cycle, then it is a bridge. Now, I realize that just the idea that coming from the definition of a bridge, if it's connected and if you remove that edge, the graph becomes disconnected, you know it's not part of any cycle, and you're like, well, this seems really, really obvious. But we still have to prove it. And what we're going to do here is we are going to prove direct and we're going to prove an indirect version. So we're going to, because obviously you have to prove both ways. You have to prove if E is a bridge, then E is not part of any cycle. And then you have to prove E is not part of any cycle, then E is a bridge. So you have to prove it twice. So first up, part 1. We are going to look at E is a bridge, then E is not part of any cycle. Okay, so we start in the proof. So we're required to prove that E is not part of any cycle if E is a bridge. We're going to prove this one directly, and the next one we're going to prove indirectly. Okay, so if E is a bridge, so we're going to start off, remember, when you prove it directly, you take anything from A and you lead it to showing that B is true. So we start off with E is a bridge. So what do we know about bridges? We know if E is a bridge, then by definition, G minus E disconnects the graph. So in this regard, G is disconnected. Either G is going to be disconnected or E is not part of a cycle. And therefore, because we have the situation that G is connected, because remember that's also an A assumption, we can then show that E is not part of any cycle. I realize that may not sound clear, so let's just discuss this once more time. We are proving this section, this part of it, directly, which means we have the conditions G is a connected graph and E is a bridge. Then we're going to use the definitions of E is a bridge and the definitions of a connected graph to show that E is not going to be part of any cycle. So let's just write down what we know. We know if E is a bridge, by definition, G minus E is disconnected. Right. Now, if G minus E is disconnected, so that's a definite situation. We've either already started off with G being disconnected, or E is a bridge. Oh, sorry. Or E is not part of any cycle, and that's why it disconnects it. So, we start off with E as a bridge, then by definition we have that G minus E is disconnected. For G minus E to be disconnected, either G must have already been disconnected, or E must not have been part of a cycle. So, for G minus E to be disconnected, either G is disconnected, or E is not part of a cycle. But we were given, and one of our conditions of A is that G is a connected graph. So since G is connected, we have the case that E is not part of a cycle. Okay, so let's just recap that again. We have our theorem, which is let G be a connected graph with E an element of the edge set of that graph. If E is a bridge, then E is not part of any cycle. So we begin with the definition of a bridge. So we say if E is a bridge, by its definition, G minus E is disconnected. So that's just using the definition of a bridge. Then we look at, okay, G minus E is disconnected. What do we know about if G minus E is disconnected? And the idea behind that is either G was already disconnected to begin with, so removing another edge from it, doesn't change the fact that it was disconnected originally, or removing that edge made it disconnected. And the only way you can disconnect a graph is if you remove an edge which is not part of a cycle. So you have those two options. Then you look at your other conditions of A, your A conditions, and you say, well, we actually say that G is a connected graph. So since G is connected, it has to be the other case where E is not part of a cycle. And now you're showing that by the definition of a bridge, you have the situation that E is not part of a cycle. Now you have to go ahead and prove the other direction. If E is not part of any cycle, then E is a bridge. So we're going to use a new page for that. So now the second part of the proof is you have to look at the opposite direction, which means you have to say if E is not part of any cycle, then E is a bridge. So let's just write that down. E is not part of any cycle, then E is a bridge. And we're going to be doing this one by looking at indirect. So when we look at indirect, remember we say not B. So in this case, B here is E is a bridge. So we're going to say assume E is not a bridge. So let's just write that down and say, okay, assume E is not a bridge. Right. Now what we're going to do here is say if E is not a bridge, and we know that G is connected, then G minus E must also be connected. So that just comes from the way we think about things. So we have the case of G is a connected graph that was given to us in A. Okay, and we're assuming that E is not a bridge. Then in that case, our G minus E should also be connected. So that is something we have to figure out and connect, and now we tell our user that. So or reader. So then we have G minus E is connected. Now we know that if G minus E is connected, there exists a walk. You have that situation of if you have a connected graph, then there exists a walk, a UV walk between every single vertex in the graph. So we're going to utilize that. So you'll also start noticing again that you need to remember your theories and your past theory and use it to build a puzzle to get you somewhere. And the reason for that is you want to get some contradiction. And you kind of want to have the situation of if E is not a bridge and you have this walk, and you remove E, then E must have been part of a cycle. And that contradicts the whole idea that E is not part of any cycle. So that's what you're trying to aim for. So we go with what we know about that. So we're like, okay, if G is connected, there exists a UV walk between, every vertex in it. So let's write that down. So we say, okay, then V1, V2, which is element of the vertices set of G minus E. And remember, when you remove an edge, it's still going to be part of the vertices set of the original graph as well. But anyway, and since our G minus our E is connected, there exists, and that's just shortened terminology for there exists, a walk, well, a V1 to V2 walk. So usually we use V, U, and V. Here we are just using V1 and V2 just to make it a little bit clearer. But they're arbitrary, so you can choose whatever you want and just make sure that you keep it. Okay, and this walk, and this is something else we know. If there is a UV walk, there is a UV path. So we have this case of, well, listen, if it's connected, there's a walk. But we also know that if there is a walk, there is a path. So again, that's two sets of theory that we are utilizing in this to try and build to some contradiction. Not the easiest thing to do when you're starting out, but it is something that you will learn to progress with and get slightly easier. It's a nice puzzle. Okay, so, and this V1, well, and this walk, let's keep this with words, and this walk contains a path via a previous theorem. Now, generally, you won't just say via a previous theorem when you're solving proofs, but again, we're just entering it, so we're just trying to get you to slowly start seeing how you connect things and stuff. So usually you'll actually state the theorem that it comes from, or state the theory that it comes from, or point out that this is something that exists. Okay, so now we have this path. So we have the path from V1 to V2 in G minus E. So we have V1 to V2 in G minus E. But we also know that we can do this approach where we go from V1 to V2, but because we can go back, so we have V1, and that is a closed path. And when you have a closed path, that's a cycle. And the thing is, when you're doing this, because it is in G minus E, you can have a situation where, that E is part of this. Okay, so V1 to V2, then to V1, is therefore a closed path with E in it, which is a contradiction because a closed path is a cycle. Okay, that little lightning bolt is technically a contradiction, which I have mentioned previously, and you can also use the upside down T. So just your choice kind of situation. And it's a contradiction as E is not part of a cycle. Therefore, our assumption is incorrect. And that means that E is a bridge. And E is a bridge. So let's just discuss this one more time. So we go through it and we say, okay, we assume not B, and that is assume E is not a bridge. Then we have that G minus E is connected, and that comes from the theory. We know that G is connected. If E is not a bridge, then G minus E is also connected, because the only time you disconnect it then is if you remove a bridge. Then we know in every single connected graph, there is a walk from any U to V vertex. So there we have our case of we have vertices V1 to V2, which is element of the vertices set of G minus E, which just means it's element of the vertices set of G, but anyway, we move on from there. And we have the case of since G minus E is connected, there exists a V1 to V2 walk. And this walk contains a path via the previous theorem. So now we have this walk, or this path, in G minus E. And then we can say that basically, now V1 to V2 to V1 is therefore a closed path with E in it. So if you remove it, so originally, if you go ahead and remove E, you still have that walk, right? Because it's connected. Now we're saying, well, we can actually double back from V2 to V1, and there is going to be a closed path with E in it, which is a contradiction because E is not part of any cycle. And therefore the assumption is incorrect and E is a bridge.